Yo yo, welcome. Today we're working on my custom operating system for x86, currently written in Rust, and currently it's pretty like a dummy little operating system right now. It doesn't do much. It can like write to VGA, it can allocate memory, it can like adjust the date and time, read it from the RTC, sets up like interrupt handlers, has async await support. So if I look at like how I'm running my main, this is actually an old version, so I can't show that right now. But all those things are ready. And what we're working on today is trying to do some like runtime code generation to improve some of the shit show that is interrupt registration. So hold on. Just let me save this and go back to where we're starting from. So to handle interrupts, what we have to do is we want like a way for our drivers to register interrupt handlers. And so they say like, hey, I want interrupt number 35, and when you run interrupt 35, call me, I'll do something with it. In order to support that, we need some sort of like runtime lookup of interrupts. But the way that interrupts are triggered on the CPU do not provide this for us. So the interrupt handlers, what happens is we give a function pointer to every single interrupt number on the CPU, and the CPU just calls that function with no arguments, or with arguments that don't give us the information what we need. And so what we do is we actually register a special interrupt handler for every single one that like pushes the interrupt number that came in onto the stack and calls this like generic interrupt handler. So basically like passes as an argument the interrupt number into this interrupt handler that then does like a proper lookup of the runtime registered handlers, right? Great. But what this means is we have to like generate code for every single one, and we generate code for every single one by just manually enumerating them all, and that sucks. So what I want to do is I want to look at runtime generation of these guys and kind of see what happens. So we got pretty far yesterday. I was looking at this runtime code gen branch, and we got to the point where we proved that we could, in fact, generate some assembly that would do the same thing that our old function is doing. And we also proved that if we manually take some of that assembly and drop it into a certain area of code, or like if we drop it into like memory that the CPU can jump to, and we like stick that in the interrupt handler or the interrupt vector and say, CPU, go to this memory address, that all works. And so all we have to do now is figure out, like, we have to assemble this into like machine code, I think is what people call it, and then make some modifications to it for our specific use case. And we got a little hung up yesterday because, let's see, where was I? Oh yeah, so here we define one for 99. Okay. So if I go in here and I obj dump kernel, and let's actually instantiate 2 to demonstrate the problem. So we'll make ones for like 90 and 99. Cargo build. Give it a sec. Obj dump. So we have interrupt handler 90, and he does something pretty sane. He like sets up his stack. He like saves some registers, and then he has this like he pushes like his interrupt number. 5A is 90, 63 is 93, 99, and he calls the generic interrupt handler. Great. Like cleans up his stack, restores registers, restores stack frame, and ends the interrupt. Straightforward. But what kind of sucks here is that these calls, even though these two functions have the same call, these are different numbers. That's because this is like an immediate call instruction. So he's saying like, call this number, basically, and this number is a relative offset from where he is in the binary. And we don't really want to calculate that information because it makes it a little hard. Like every time you move the the generated code around. You have to like update this number, and that would be a pain in the ass. And so we were struggling to find some form of like absolute call, and we did have one. Hold on, I clicked the wrong window. We were using this like let's see, call x86. We were trying to use call far, which is just like gives me an absolute address, or maybe we're trying to use these. We were trying to use a way. Here, let's just show it on here. We were trying to use this instruction, which is like a long call, which is like go to this absolute immediate address and use this like set of use this like segment that defines our like execution environment and permissions and stuff. But we couldn't get our like arguments past this way, and I kind of gave up and said I would like read about it off stream, and I did a little bit, and I think basically that's just a complex call, and it's probably doing some stuff I don't understand. But I did realize that there's these other versions that have absolute and absolute addresses given in registers. So what we can actually do here is, okay, I'll show the failing case. So the failing case was, I think, this, where we call this guy. And here we see like no handler for interrupt 8 printed out on the screen, which is odd because we're trying to register interrupt 99. But when we do the old way, where we just say call relative address, we see no handler for interrupt 99, and we return correctly. So clearly something's wrong there. And what we can actually do instead is we can do a move of generic interrupt handler into a register, and then we can just call that to jump to the address in that register. I think this is the syntax. And if I cargo run this, that works. And if I look at the disassembly for the two versions of my function, these are in fact just like the same bytes, which is just the absolute address of this function, which is great. That's what we want. And so what we can do now is we can use this as our reference for how to implement this. Which is this guy here. We'll just align him, maybe indent these guys some more, or maybe we'll just delete this, and we'll comment this, and we'll do, now we just have to extract like the actual info here. So this here is like the human, quote unquote, human readable assembly. So this is like the instructions that are being run on the CPU, kind of. I think actually, yes. I think these are just the instructions that are being run. And these are the like bytes in memory that the processor is going to parse. So these like are like an encoded version of this, basically. And so what we want here is we want the machine code version. So we'll just kind of like rip these guys out like this. And then we'll put these all on one line. And we'll make them hexadecimal. Oopsies. Hexadecimal and comma separated. Okay, I don't know what I just did something that I've never done in Vim before by mistake, but I liked it, so that's pretty cool. And this is a template that's probably like U821. It's probably longer than this now, but we'll let the compiler tell us how many bytes it actually is. And now we just need to confirm that these offsets for where are we going to inject the number that we're pushing, so this guy, that's at byte 0, 1, 2, 3, 4, 5, so this is good. And then the address at 6, 7, great. And the address is little endian encoded, smallest byte first, great. And that's what we're doing here. So theoretically, this should just work now. So if we, instead of doing these guys, use these interrupt stubs, which down here you can say interrupt services routines for this index equals generate interrupt stub for this index. Then here we use ISR's I. We take the address of that, and then we cast it to a pointer so that Rust doesn't get mad at us. Which is like this. Or maybe we can do as pointer. And then we cast the pointer to a U32. Great. This needs to be a USI or U8. And do we compile? We do, and do we run? Okay, so now we're spamming a number here, and I think that's because in our interrupt handler, generic interrupt handler, yesterday we had some debugging fog. Great, print line. Get rid of that shit. And there we go. So that was pretty straightforward. And yeah, it was just missing one little trick. So I think we're like basically done there. Let's just do a little bit of cleanup and maybe try to oh, there's one more thing I wanted to look into. And it was that I think that everything in here can be done at compile time. I think. So I think that we can like pointers can not be cast to integers during const eval compile time. Pointers do not have an integer value. Avoiding this redirection via or raw leads to compile time on behind behavior. Okay, so we cannot do this at compile time. I was going to say that as long as we know this address, which I guess we also just don't at compile time, we don't know until link time what this address is going to be. We could just generate this all up front, but we can't. So we'll do it this way for now. So let's just make sure that we're in like a good state here. So let's get our linter script passing. Unused imports. And no error. Sorry about that. We'll delete this. Cargo Clippy, cargo format, cargo run. And I think everyone's chilling. This is no longer unused, so he should be ISRs. And I guess this should go up somewhere with the rest of our statics. All right. So that's a lot nicer, right? Now, instead of that like massive block of code multiple times, we just have this like nice little for loop. Easy peasy. So I think we're good here. So let's get status, get add u, get commit -m, smiley face, and now we just need to rebase him to squash everything down into one commit. Squash, and we'll call this I'll fill this in more detail later, but we'll just say interrupt handlers now work runtime generation of interrupt handlers. Yeah, okay. That's good for now. And then I just wanted to rebase this onto master just to see. So let's just make sure that master is up to date. So let's just put this onto master and make sure that everything's still good. So here, we're just going to want B. Okay. I guess we just get rebase continue, and we cargo run again to see if everything's still good. And it's not. What doesn't he like? It's because I'm trying to print in the interrupt handler. And it does not like that. And these should be panics anyways, so we're good there. Okay, so we're booted, we're running, we sleep for 3 seconds, and we halt exit. Cool. So everything is done. So we can just call this done. Quickly Commit that. And now we're looking at PCI device enumeration. So let's just write this down. This is at around 15 minutes. This will help for YouTube timestamps later. And there we go. Now we're on PCI device enumeration. Very cool. So let's look this up. PCI on the OS Dev Wiki. So the reason I want to get PCI up and running is because, how do I say this? The eventual goal here is to do something quote unquote useful. Useful is a little strong, but I do want to get to the point where I can like maybe run a web server or something from my operating system and like interact with it. And so when I look up like what's like the fastest path to this, there's this Ethernet driver. I think it's called, I'll probably find it on just the main page here. Hold on. This guy. There's this Ethernet driver that is heavily supported by like qemu and just like virtualization environments in general, and is simple, which is the thing that we're really looking for here. And this is like a PCI card that's plugged into that we can like ask qemu to plug in for us. So I think let's see, qemu network card. Here we go. Give it a sec. So this guy here is a command that we can pass in to say, hey qemu, please give me this this network card, the 8139, which you see here. And then we like use this for networking in general, I think. I don't really understand like the rest of this command, but that's okay. So let's start there, where we ask qemu to give us a PCI device, and we can actually start giving it things like bus equals PCI 0, adder equals 0. So we can give it like a specific PCI address, and that will make our initial development of this go much easier, I think. So let's cargo run. And PCI slot 0, function 0 not available because it's in use. Sweet. So we can just give it like another number. So let's give it like 1. Is that in use? That's also not available. 2. Not available, used by VGA. Okay. Sweet. So we now should have something at PCI 0, adder 3. And we also just learned by doing this that we have PCI devices at 0, 0, 0, 1, and 0, 2 as well, which is sick. So that means that if we start trying to do PCI probing, we'll know that we should get stuff there. But yeah, we got distracted. So why are we doing this? I want to do networking, and as a prerequisite to getting networking up, we need to have PCI support, or else we won't be able to talk to the network card. So that's what we want to do today, is just get like some sort of proof that we're working, that we can like talk to PCI devices. So we'll say that we want PCI device probing, enumeration, interaction, etc. So probably the first thing that we want to do is say anything to a PCI device. What does that mean yet? I don't really know. So I was reading this a little bit earlier, and it looks like we can talk to PCI devices through port IO, and the first location, 0xCF8 is the config address, second 0xCFC is the config data. So theoretically, we should be able to find a way to talk to things between these two. Config address specifies the configuration address that is required to be accessed, while accesses to config data will actually generate configuration access and will transfer data to or from the config data register. So if I understand this correctly, each device has an address, and we talk to it by we talk to any individual device by first writing that address, then trying to talk to it. And we can actually confirm this here. So PCI config read word. And they're saying that given a bus, a slot, a function and an offset. So slot we did not punch in here. I wonder if we can put this as part of our PCI device settings here. So if I say slot equals 0, does this get mad at me? Slot not found. So maybe PCI 0. Okay, so what is the slot? Okay, but here we say we have this like bus number, device number, function number, register offset. So I think that maybe adder is the device number and function number is something that we have to figure out later. So we have bus slot 0, 0. Right, okay. So I guess functions are just numbers that we can put in here. I think I saw that somewhere where like this snippet here, where is it? This one? This indicates that we get the vendor by reading bus slot 0, offset 0, bus slot 0, 2. So I guess function 0 is like probing. All PCI compliant devices must support the vendor ID, blah, 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 type fields. Implementation of other registers is optional. So, okay, let's assume for now that we can just kind of work with this. Now, I am a little curious, what is function? So there are multifunction devices behave in the same manner as normal PCI devices. The easiest way is bit 7 of the header type field. If set to 0x80, the device is multifunction, else it is not. Make sure you mask this bit when you determine header type. Okay, so I guess those are like device defined. So we can just start by, first let's look at this PCI config reword. We'll probably need some sort of like PCI device abstraction in our kernel. And probably what we'll do is we'll construct PCI devices that own their own bus and slot numbers. And we'll allow reading and writing them. But maybe it makes more sense to get to that later. I guess the first step is just write this in general. And I think this is pretty easy. So let's go to main. And what I'm noticing here is that these are using like 32-bit reads and writes, which we don't support right now. So that's step 1 is support 32-bit reads and writes to I/O. So if I look at my I/O ports, I have this like read B and write B command, which are just 8-bit values. And I think that these longer versions are just the same, but they take in 32-bit values. And let's just double check this like out assembly instruction. So I know that for before, we had to specifically request register DX. Because sorry, DX for the address and AL for the value, because I think that the assembly instruction like required that. I don't really understand why. Maybe the like registers are hooked directly into the lines or something. But let's quickly do a quick read. So these do in fact still require DX and EAX. So DX is output word to address in DX. Right, so we can just replace this with EAX instead of AL. So I think we say AX here, and then EAX. Oh, this is the wrong one. Oops. So write L, this is going to be EAX. And I think we just can write EAX in here. And for read L, this is going to return a U32. And here we ask for EAX. And then I think that's good to go. So we'll just put a question mark here in the to-do because we think it's done, but we haven't actually tested it. And now we have what we need to implement PCI config read word. So let's just get into main and start hacking shit up. So probably we want to initialize our kernel and then run this shit after. So let's kind of restify this. This is a function, PCI config read word, and this takes in a bus that's a U8, a slot that's a U8, a function that's a U8, and an offset that is also a U8. Yep. Seems reasonable. So here we're going to do this differently. We're going to say address is 0, and we'll say address right. I have some like helper functions, just like set bits. I think it's set bit. I probably have to use our utility class here. So, oh, this is weird. These guys should be in here, and this guy should also be in here. Probably my sorry. It's probably my auto completion, like just injected that at the top of the file. I think that's where it goes, but really stuff that's like part of the crate should be flagged as part of the crate. Okay, there we go. Sorry, I got distracted. Okay, so in our utilities, we have bit manipulation, set bits. And this is a trait that we can use to write to U32s and just call this like set. Let's look at what the functions on this are. Set bits. And so here they're saying we have the register at bits 0 to 7. So I guess here they're calling offset register. And why are they ending with this 0FC? Okay, that's fine. We'll figure that out later. Function is bits 0 to 10. So this is L func shifted left by 8. This is concerning. So they don't actually do any like validation that we're only setting those. So if the function number was too high, we would clobber here. So, but that's okay. So here we can say that 8 bits up. We have 2 bits of func. And this is 11 bits shifted. We have 11, 12, 13, 14, 15. 5 bits, is that right? 0, 1, 2, 3, 4, 5, 6, 7. Yeah. 11, 12, 13, 14, 15. 5 bits is weird, but we'll take it. So this is the slot at bits at 16 to 23, which is 24 minus 16 is 8. We have 8 bits of bus. And I'm assuming 31 we want true. We just want this to be set. And we'll just say this is offset. Now, what I don't understand is why this is ANDed with 0xfc. This is the enable bit. This 0xfc is odd to me. So why is that? The least significant byte selects the offset into 256 byte configuration space available through this method. Since all reads and writes must be both 32-bit aligned to work on all implementations, the lowest 2 bits of config address must always be 0. Understood. So instead of anding it, like just like blindly healing it like they did, what I'm going to do is I'm going to assert that offset assert equal that offset and 0b 11 is 0. And then we'll say PCI reads must be 4 byte aligned. Yeah, and aligned. Yeah. Okay. Cool. So now we actually also, in our implementation, will need the port. So port is a mute port. Mutable because we wanted to ensure exclusive access on the ports. We said it was mutable. And now here we should be able to say port write L 0xC F8. Oh, we don't. So 0xC F8 will be reserved later, and we just pass in address. There we go. And then they read in the data. Offset and 2 times 8 equals 0. We'll choose the first word of the 32-bit register. What? Offset and 2. So this is saying we'll choose the first word of the 32-bit register. What the fuck are they doing? Shifted right by. So they read the word and then do some crazy shit to it. What's happening? The least significant byte selects the blah blah blah. Since all reads and writes are about 32 blah blah, the lowest 2 bits of config address must always be 0. With the remaining 6 bits allows you to choose each of the 64 32-bit words. If you don't need all 32 bits, you have to do unaligned access in software by aligning the address followed by masking and shifting the answer. Oh, this is because this is read word, but we should just say read. So it's because they want to read 16 bits, and so they're doing a 32-bit aligned read and then masking out the part that they want. Sure, with just something fucked up math. So we can just port read L. Baby. And here we'll just return a U32. Cannot find port, so in main we need to now import port and port manager. Or temporarily, since this is like test code. And this write L takes an U32, so what's he mad about? Oh. We need to cast this to U32 over here. And all of these need to be cast to U32s because that's what the API of this like set address needs, whatever. I think it actually doesn't matter because both, like no matter what we load into the same register, there's like 8-bit, 16-bit, and 32-bit modes of the register, but I think all of them like are the same cost. I don't actually know that, but that's just like my intuition there. I'm sure I'll be proven wrong eventually. Okay. So we have to actually call this function somewhere. So let's say where do I want to do this? Here, instead of doing our demo, we're going to request a port. So this is kernel port manager. Let port equals kernel port manager request port. And the port number is 0xCF8. And this is the config address or config port. And we need the data port as well, which is CFC. And then we need to go back into this guy and actually take in both the config port and data port because I messed this up. So we just do this, right? And down here, we write the config port and we read the data port. Easy peasy. I think that's right, right? So let's just double check. Config address, CFC. CF8 is config, CFC is data. And then here they write to config, read from data. Solid. And now we can just call PCI config read. We pass in config port and data port. And let's just try reading 0000 and see what happens. And we'll print this in hex, I guess. And see if we see anything interesting. Cargo run. So we did get a number back. Is it a consistent number? Yes. And if we then choose to read bus 0, I think it's slot 1. Do we get the same thing here? So before it was 7FDF-E86. 7FDF-E86, which is a little concerning. I would expect different things for different slots. But let's see, what is this supposed to be? This is supposed to be the... Where did we go here? This is the vendor, and this is the device. So where can we see this? Here we go. Vendor ID. So this should be vendor and device stuck together is the first 32 bits. So can we do bus 0 slot 3? Oh, that's something different. And does 4 fail? No. What if we do like something crazy? Like, just get way out there. So we are getting something back every time, which kind of sucks. I was kind of hoping we'd have some sort of proof. Can we like maybe find out what the vendor and device ID of this guy is supposed to be? PCI vendor ID is this, and device ID is this. Here we go. So if we find this device correctly, we should find 183910EC somewhere. Oh. Hold on. Let's just double check. So all these are in fact uint 8s. Okay. Let's just double check that we are doing this right. So config port is 0x CF8 and data address is 0x CFC. So let's think here. What can we prove? We can look up we can like try to figure out what's plugged into qemu PCI ports. Qemu default PCI devices. PCI IDs for qemu. Maybe this is useful. So does what we're reading look anything like any of this? FE86. No. Okay. Well, let's maybe try just spamming the whole port range. I think I saw something in here earlier about doing a brute force scan. Here we go. So here we're using function 0 everywhere. They're calling get vendor ID bus device function, which I think we saw here. I guess we should look at the vendor and see if we can find any that are 0xFFFF, because that would confirm this seems to be like a flag that indicates that it's not there. And if we don't see that, then that means we're not talking the way we think we are. So let's see. All PCI devices except for host bus bridges are required to provide 256 bytes of configuration registers for this purpose. So let's try to do this brute force scan where we go over each bus and each device. So bus or bus num in 0 256 and device num in 0 256. Check device. We will just get the vendor ID for now. Let vendor ID equals PCI config read with the config port, data port, bus num, device num 0 0. And since the vendor ID is the lower 16 bits, we can do this. And let's print out the vendor ID. That's pretty funny. So for uint8s, you have to do inclusive ranges because it can't get less than 256 or it'll run forever. So the fact that every single one of these is FEFF really is pointing me to something being wrong. But I don't know how to confirm that. Okay, let's see if we have to do something special here. The PCI bus. By combining transparent upgrade path from 132 megabyte, blah, blah, blah. Okay, let's... I should finish reading this. 5 volt, 3 volt, PCI bus needs low-end desktop systems and high-end, blah, blah, blah. So they are just talking about the configuration space. This seems to work. It doesn't seem like I need to do any setup here for each target. Oh, maybe I do need to initialize PCI devices. So how do I enable them? Here we go. So somewhere here, class codes, base register, blah, 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 blah. Detecting configuration space access mechanism. So let's see if number 1 works. So for BIOS systems, we can interrupt 1A with 0x with AX equals B101. So I guess that's a way to interact with the BIOS. But we have overwritten our interrupt table at this point. So they talk about you can do some manual probing. IO port access might have undefined behavior. Or accessing IO port 0xCF8 is the same as accessing IO port 0xF8. Okay, so let's see if we've done something here. DX is the address that we're writing to. And have we done something fucking stupid where DX is the 8-bit version? No, I'm pretty sure. So DX versus or AL, AX, EAX. Let's just double check. AX is the lower 16 bits. Good. So we're fine there. Let's double check these write L and read L's. So the fact that this says AL still is a bit concerning. This should say EAX. DX is still good, so maybe that's the problem. Hey, there we go. So we just fucked up the 32-bit port read. And what we actually want to see is a bunch of FFs. Okay, that's sick. So what we can do now is we can say let vendor device vendor is this. And we can say if vendor equals device vendor and 0, or we call get bits even, which is here. Get bits are nice little avoid bit shifting functions, where presumably this guy is shift and length. So 0, we have 16 bits that we want to get into here, and device is 16-bit shifted, 16. And we say if vendor is not equal 0xFFFF, let's print this bad boy like this. Cargo run. Oh, let's go, baby. So some of these look suspicious, right? Device ID 11111234. But we are looking for 813910EC, which we see right here. So I think that we have proven to ourselves now that we have access to this PCI card. So I guess now we understand this a little bit. I think I want to keep going down this just like experimentation path before we start figuring out like what our code is going to look like, because I want to see what like talking to a device looks like. So here he has like registers. So let's see. The IO base address and the IR key for the device is taken from the PCI configuration. So let's look at PCI configuration. We have general devices. Here we go. And here, these are probably IO space addresses, maybe? I guess okay, so first we check the header type. So this is a common header. And then based off the common header type, we can parse the full header. So let's do that. Let's read what these are. Device and vendor ID. So vendor is like a company, I think. Where valid IDs are here. These do look like companies. Yes, like Asus has one, like probably AMD has one. 4130. And probably since I have an AMD card, I think I can probably check devices. I think it's 03000. I don't know how to... Yeah, so this is my AMD card. And can I check, like, the vendor ID? Vendor. So I have 1002, which is this. Yeah, so this is, like, vendor is, like, company name. And presumably... device is which card I have, like which device it is from that company. Okay. Status is register record status information for PCI bus related events. Okay. If I click this, does it bring me somewhere? Oh my god. Ah. So this is a lot of info. Let's ignore that for now. Command. Provides control over a device's ability to generate and respond to PCI cycles. where the only functionality guaranteed to be supported by all devices when a 0 is registered to this register, the device is disconnected from the PCI bus for all accesses except configuration space access. Okay, I see. So this isn't a like header per se. We can actually like write to these and stuff happens. Gotcha. Class code read-only register that specifies the type of function from the device platform. Okay, so here, this would be a way for us to like detect, is this a networking device, and maybe like choose which drivers we want to use, etc. Or maybe it's just metadata that we don't really care about right now. A read-only register that specifies a register level programming interface that the device has, if any at all. All right. Revision number, sure. So these doesn't matter. Probably what we want is like the juicy stuff is in header type. Right. So where you have a generic address and they start talking about like these generic base addresses. And I think I remember reading somewhere that these addresses are in like physical memory, DMA, maybe? Base address. Can be used to hold memory addresses used by the device or offsets for port addresses. Typically, memory addresses BRs need to be located in physical RAM, while IO space can reside at any memory address. Sure. You can check the value of the lowest bit. Aha! Okay. Cool. So, what we can do is we can, let's first look for the RTL device via its device and vendor ID. So, we can say, we can create a function that's like find RTL 8139. And we're already seeing that we're going to be passing these guys around a lot. So let's actually make a like PCI device struct. Or we'll call this PCI bus PCI, just all PCI. And he has config port. And he has data port. And now we can say impl PCI function read. And this is just this function, but we take in self. I'm trying to avoid all this extra parameter passing. Okay. And we take in bus, blah, blah, blah. So this is just, we throw some selfs on here. And here we'll say let PCI equals PCI config port data port like this. Solid. And then we have PCI this. And I guess this guy can just be called like config read. Okay. So here we replace this with PCI config read. And now let's find our device. So we'll say find device. And we'll take in our self by reference, mutable reference. And we'll say vendor is a U16 and device is a U16. And I guess here we'll return its address. So we have like struct PCI address. And here it's a bus U8 slot U8. So here we will return a PCI address because we found it. And if it's not there, we will return none. So we'll have an optional address. And now, temporarily, we'll just do a brute force scan for it. We could do this brute force scan one time ever and keep a list of them. But for now, this is fine. And here we delete some of these extra arguments. Okay. Okay. And if vendor equals vendor, oh shit. We'll just throw some devices under here. Crap. Probed. We'll call these probed. If vendor equals probed vendor and device equals probed device, then we return PCI address, some PCI address, because we need to flag that it's the correct one. And we'll call this vendor or bus num slot device num. There we go. And otherwise, we return none. We did not find it. As U16 for both of these guys. Okay, so now we should be able to say let our RTL address is PCI find device, and we know that the vendor ID is 0x1 of EC, and the device ID is 0x8139. These guys are not end mutes here, they're just part of the struct. And we will print line the RTL address in debug. Okay, and now we need to say that this is a debuggable struct. This. And if we cargo run, we just need to quickly drop one of these mute boys on here. Okay, so we did in fact find the device, and now let's get a little crazy and let's change the device, the bus number and device number, and see what happens. So if we say put me on bus 1, baby, there isn't a bus 1, but we can put this on address maybe like 123. Too high. Let's try like 78. Too high, 16. So I thought that if I increase these, they would stay matched, but it looks like past a certain point, they don't. Oh, probably this is hex. So this would be 17. Cargo run plus 17. Yeah. So the address is taken in hex. Got it. Okay. So we know now, we have confirmed that our scanning code is working correctly, because as we change the slot in qemu, the PCI address does in fact match. So we now have access to our device. So here we can say find, what is this thing called? RTL device. And we can say that this happened approximately 58 minutes into stream. So that later, it's easy for me to find where things happened. Okay. So what's next? What's next? Now we probably want to confirm that this is in fact a generic object, so we can register 0x3 from that address. And really it makes sense. Nah, whatever. Let's think. So what would be nice is if we could have like functions on here. They're like read register. Right? Like, and this like just returns a U32. Because I don't want to like have to like convert this address back, etc., etc. So I guess we take in a PCI, right? Because this, we can't be writing multiple at the same time. And we just take in a register number. It's a U8. And this just calls PCI config read with self bus, self slot, 0, self register. And this isn't self, this is just register. Very nice. So let's now, when did I write this guy? Find RTL. This doesn't look familiar at all. I'll just delete that. Okay. So we've found the RTL address, and we say RTL address, read register. Oh, we have to unwrap this. Assume that we found it. So now we have this read register command, and we pass in the PCI bus, and the register is, we were trying to confirm that the header type is in fact 0x0. So we can say we want to read register 3, and oh, okay, so this is confusing to me. Register. So the register number is not the same as the offset. So that actually explains a lot. So this should be register times 4. Because the registers are just addresses that we poke that are 32, each register is 32 bits, so we're 30-bit aligned, blah, blah, blah. So we'll read register 3, and we only care about bits 16 to 24. Okay, so we say let RTL header type, and we'll say we expect it to be anything but 0. In reality, we expect it to be 0, but we want to prove to ourselves that we crash if it's not. So here we should crash. Good. And here we say we expect ourselves to be header type 0. Great. And now we can start reading this as a generic address. So let's parse out the base address, because this is how we start talking to this guy directly, right? Womp, 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 womp. So turning on this guy, blah, blah, blah. First you need to enable PCI bus mastering. Choose you can read the command register from the device's PCI configuration space. Okay, sure. Blah, 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 blah. I see. So the reason, there's like 2 address spaces here, I guess. There's like PCI, who has like generic things about working in like PCI itself, but then you ask the PCI space, like, hey, how do I talk to you? I want to talk to you, not like your PCI config, because you might have like your own functions. And so that's probably what these like base addresses are for. Let's just read a base address and kind of see what we get. So here we can say base address 0 is the 4th register, and let's actually just read all the base addresses. So for 0 to 1, sorry, this is 0, 1, 2, 3, 4, 5. So we want to read the first 5 registers. Let's just see what these guys print. Presumably there will be some sort of like sentinel value for if they don't have that base address. But yeah, let's just see what these look like. So I think I put colon number X here to say print in hex, and let's just print the base address. Base badress, no, I want an address. And we'll just put the number here as well. And I guess this should go after this. Right. I just forgot to write a word here for in. Okay. So yeah, this indicates that there are two address spaces that I can talk to for this thing. I assume that one of them is like device configuration, and one of them is probably the data that's in the Ethernet controller itself. And let's see, there's IO adder. Here they just use IO adder on the RTL, kind of just generally. So I wonder, the fact that there are two is a little odd to me. Are these consistent? They are consistent between runs, but maybe that doesn't tell me anything because maybe qemu is like initializing all of its lines correctly every time. So IO base address. Okay, let's see if these, like, anywhere somebody will tell me about BAR. Can be used to hold memory address used by the device, offset ports or addresses, blah, blah, blah. So, are these guys the same? Aha! So, one of these is telling me that I have M-mapped IO, and one of them is telling me that I have IO space, because here they're telling us that there are two types of bars. One is in memory space where the bottom bit is a 0, so that would be this one, and some in IO space where the bottom bit is a 1. And so theoretically, if I understand this correctly, if I interact with this thing through either memory accesses at these addresses or config port-based IO at these addresses, I should get the same thing. And theoretically, again, I say theoretically to say, like, I don't know what the fuck I'm saying in reality. But if I understand this correctly, I could, if I understand this correctly, memory space should be faster because I don't have to, like, disable memory access in order to access the IO bus. But maybe that doesn't matter since I only have one CPU. Or maybe with multiple CPUs, you can do it separately. I don't know. I've heard port IO is slower. So, we'll test this for now. So let's maybe start by trying to talk to this bad boy through the config mechanism. And then maybe we can flip to the memory mechanism and see if that changes anything. So, let's see if there's any way to just, like, test that we can get anything interesting from this guy. So here are the registers. Mac 05, Mac Mar 07. Ooh, okay. So if we read register 0, we should get the MAC address. Okay. So let's see if we can, like, set the MAC. Dude, searching MAC on qemu. Here we go. Let's just kind of trap this guy in here. So, qemu wrapper. How do you think I can just set this on the RTL maybe? Just kind of drop this guy in here. Okay, that's good. So, let's try to just read the MAC from the device. And if we can read it, then we're chilling. And we can try reading it through both mechanisms to make sure that we understand. So here we go. Let's look at base address. Okay, so we're getting into the kind of area now where it makes sense to pull out a we'll do this on the PCI address. So we'll say find base adder, find port base adder, find IO base. I like that. We're finding the port, the base port number for this guy. Nice. Find IO base. And here, I think we just don't need to take in anything. And and we just kind of copy paste this code up there. So here we said for I in 0 to 5, we read this, but first we need to read the header type, so we'll just kind of take all of this in. So how do we want to do this? So you could argue that like this should be a function that's available for only generic PCI devices. Sorry, what was it called? With header type general device. So maybe it kind of makes what would be kind of fun is we could say I'm not going to handle this right now. I was going to say you could write like a function like upgrade, and this would turn into like PCI device, right? And maybe your like PCI device is like an enum that implements these guys types. So he's like general PCI device, or PCI bridge, or PCI card bus bridge, right? And then you could like switch on the header type and turn into these guys and have functions that are only implemented on the ones that matter. And I was going to say I'm not going to do that, but now that I've written this, it's really easy, so I'm actually just going to. So I can say grab the header type and match header type. This can be a result, and this can turn into an invalid header error. Struct invalid header error, and we could fill out the like error definitions for this later, but we just need like a type to attach this error to. So we have self, we read the register. We have to pass in the PCI ports, so we do this. We read the register, we get the bits, we have the header type. And now, if our header type is 0, we return general PCI device, general self into, or something, right? And this turns into PCI bridge. And I guess these guys, for now, just convert back into themselves because I don't actually have anything I want to implement on them. So we can just do this, PCI device, and this is a PCI device, PCI card bus bridge. And anything else, we return error invalid, like this, invalid header error. And all of these guys are okay. I'm A-okay with you. Am I right? Okay. That's arrow isn't supposed to be there. And now we're kind of chilling for the most part. We can maybe put this guy's implementation down here. And we can say that a struct general PCI device has a PCI address inside him. And here we can just say general PCI device adder is self. Okay. Okay. So now IO bases are only valid on general PCI devices now. So we can start attaching this function here. And here, we don't have to have this assertion anymore because the type system enforces this behavior. And here we can pass in self adder read register. Find IO base requires the PCI subsystem still. the PCI config space, I guess we can call it. And here we find the base address, iterating over these, and if base address get bit 0. Where did they talk about this again? BAR. Bar. Where are you at, Barry? God damn it. Okay. So the memory space is bit 0 and this is bit 1. So if this is get bit 0, this get bit should actually not return self. You should return a bool. Okay, there we go. Do I have get bit used somewhere else? This is the, I've never used this guy before. So, oh, oops, I also have to, there's, oh, sorry. The implementation has this, and this also has to return a bool. Okay, there we go. So I can say, if bit 0 is set, we can return base address. And this will return an option. It's not an error if it's not there. If it's greater than 0 and base address is greater than 0, we return 4 bundle line addresses. So base address and 0xF, but then we take 2 bits off, so I was going to try to figure out this hex value, but then I'm like, I'm not that smart. God, that's embarrassing. Okay. So this guy returns a U32. And here we need to set somebody once told me. And then here we return none. Solid. So now we can let RTL general is RTL address upgrade. We expect this to succeed. And here, if he does not succeed, we can, if he succeeds, and we expect him to be a general device. So we extract the value from the general if it's there. Otherwise, we say panic, what the fuck, RTL device was not general. And I'll take this WTF out because I'm going to forget about it later. Now it's complaining this doesn't implement debug, so let's derive debug here really quick on this guy, on our error type. And we're chilling. We are chilling. So now we can say our general device, we want to find the IO base using the PCI configuration space. And we will also assume that this is, how do I say this? We will assume that this will succeed for now. And let's check out what our IO base looks like. So let's hex print it. 0x0. Fuck! Okay, so I made a mistake somewhere. So here, I need to do base address get bits This is 30. So we shift 2, and we want 30 bits to shifted. And we need to make sure that these are greater than 0. So it's weird that I'm still getting 0 here. I thought that this if statement should ensure that I don't. So let's just take a quick peek here. And my print function is asynchronous, which I think was a mistake now that I'm in this world, but for now we just have to propagate this async around. So get bit 0, is this returning the wrong thing? Get bit. I would think that this guy is correct. So can we maybe run my tests real quick? And just make sure that this, after the API change, is still working. So these should be false. These should be false. This should be true. And those are still passing. So why, if get bit 0... Okay, let's double check this. So base address get bit 0. And this guy should be also being print. Cargo run. So this is in fact set, so that's good. And now, for some reason, is this not triggering? What's this guy say? What's he say? Yeah, so this is true and above. So these, I should be returning some base address and this. Let's see if it's this like and that's fucking with me. Definitely. Definitely. But why? Oh, I'm an idiot. I am an idiot. It should be, because I'm only masking out the lower like 16 bits or something, or 8, which is just stupid. So I should be doing the inverse of 0B11. That'll mask all bits except for the lowest 2, which is what I want. Nice. There we go. Got my IO space address. Solid. So now that I know where I can talk to this guy, I can request that port, probably. So I can say, port manager, give me a port to IO base. And we'll assume that this works. So we'll call this RTL base port. And I think that if I just read that base port, I should get the MAC address. So we'll say RTL base port.readL, and we'll print out what we get, which is, we can print it in hex, and we should see the MAC address that we punched in our qemu command line. I think. How come it says that this is a mismatch closing delimiter? Am I crazy? Oh, because I wrote a curly brace over here like an idiot. Okay, so IO base, we need to make sure that this is a U16. So we can assert for now that IO base is less than, I think there's probably like, how do I get like max values in Rust? U16, let's just see if he says somewhere. U16 max, it's just here. So we assert that he's less than or equal to U16 max. You can convert into a U32. Shut up, I'll just cast it with that. And here we go, we cast it to a U16, we make it mutable, And let's see if we get the MAC address. That, not sure if this is right. First of all, this is a 6 size, which is longer than the 4 byte size I get from a read. I will think about that in a second. Let's check what I punched in the qemu wrapper. So here, let's just zero this out. Oopsies. And I'm definitely not getting that. But what's interesting is if I change it... Oh, what the fuck just happened? When I change these numbers, I get like different behavior. Okay, so let's see here. 3, oh. I'm seeing 3s. I'm seeing 3s. Oh, I'm seeing 2 3s. Okay, that's a really good sign. Okay. Okay, so all this matches up. So I'm getting the first 4 bytes of the MAC, or the lowest 4. Interesting. It looks like it's going, like, not in the order I would expect, but I definitely am getting MAC address from here, which is very, very cool. Very cool. So here we can say that we have read MAC. Let's try to get read MAC address working from RTL with IO ports, because we know that we're close here. So we want IO base plus 1 as well, and we'll call this RTL port 1. And this is 8 offset, I guess. 4 offset. 6 offset. Huh. Okay, so what's kind of fucked here is that the IO ports, like my port mechanism, is like clearly broken. Because if I request an IO port, I need to specify like what range of values I'm allowed to read from it. Because these are like just addresses. Each of these ports is just an address, really. And if I can write to these ports as 32-bit values now, it means that if I request a 1-byte port that's next to a 4-byte port, like those will clobber each other, and the port manager should not allow that. And so really the port manager should actually hand out different port types based off of the size of the port that's been requested. So we'll throw a fixmin in here and say that 32-bit ports adjacent to 8-bit ports can clobber each other. Fix in type system. Okay. Okay. Let's get going here. So let's for now ignore that problem for now. We will offset ourselves by 4 bytes because that's all that we could read here. And we'll also read port 1. And so now, if I go into qemu wrapper, if I set all 3s, I should in fact see that the first 8 bytes are here. So if I now say I want my MAC address to be 1, 2, 3, 4, 5, 6, 7, 8, 9A, BC, I do in fact see that. See 1, 2, 3, 4, 5, 6, 7, 8, 9A, BC, which is sick. We've just proven that we can read this out. Now, the reason that these are backwards is because we're reading them as 32-bit little endian numbers, and that's not how the MAC address is stored. It's just stored as like sequence of bytes, but that's sick. And so now what I want to prove is if I do the same test, but with the memory base, I should see the same thing. So we have find IO base, and we can say find mmap base. And here we do the same thing, but instead we check that this is not 0. So it's the same loop. Take these print lines out. And for memory, where are we now? Where are we now? Okay. Bit 0 is always 0. Bits 2 to 1 is type. Okay, so the memory space can have types. Typically, memory address bars need to be located in physical RAM, while IO space bar can reside in any memory address, even beyond physical RAM. Check the value of the lowest bit. The type field of the memory space bar layout specifies the size of the base register and where in memory it can be mapped. If it has a value of 0x0, then the base register is 32 bits wide and can be mapped anywhere in the 32-bit memory space. A value means the base register is 64 bits wide and can be mapped. A value of 1 is reserved for the region of blah blah blah. When a base address register is marked as pre-fetchable, it means that the region does not have read side. So I'm assuming that memory they're talking about here. If I have paging, then I ask the CPU to like move memory from like this physical area here to like this virtual area over here. And I guess they're saying that the bits indicate that there might be some values that say that you cannot map. But I guess everything is here. It's weird that every single option here says that they can be mapped anywhere in memory space, but whatever. But we have no paging in our operating system right now because we're shit. So we can probably just use these memory addresses just directly. And so this is the 4-byte aligned base address. 16 bytes, sorry. And so here we do the same thing. And we want I guess here we don't need to do this like bit shifting thing. We just say if the base address is bigger than 0. And let's do this. So we'll say print line, doing it from IO. And now we'll say doing it from memory. And to do this, we get the memory base. And find a map base. These are no longer asynchronous functions. And let's say we print out memory base 0 to 6 as a slice. Right? So here we're basically saying that the first 6 bytes we get here, I want to see those bad boys. Cargo check. What isn't it like about this? If I intend to print, you can escape it. I did not intend to print. Oh, does this have to go over here? Okay. Cannot convert index into a value of type U3. Oh, so here we just could cast this into a U8 array. And then somewhere I think that they say like the size, memory limit here, base address. So how do I know how long my configuration space is? We don't. That's okay. So we'll just say Mac. Well, maybe somewhere they do, but I don't because I haven't read it yet. So we'll say core slice from raw parts, and we'll take in the memory base, and we'll say this is 6 long, and then we'll print the Mac. And let's see if that gives me the same thing. Oh, mwah. Whoa, that's so fucking sick. Look at that. So we've proven to us. Oh, that's so fucking cool. So we've proven to ourselves now that we have PCI buses up and running. And we've rid the MAC address from RTL with memory. So we've proven that we can do this both through the IO port mechanism and the memory mechanism. And that proves to ourselves as well that we understand like what the fuck we're seeing out of these base address fields. And so I think that we're like kind of like just set up at this point now to just write an RTL driver, because we're kind of set up now to see, we know what registers they have, and we know how to interact with those registers. Yeah, so that's sick. What we need to, so what, yeah, I think I'll call it there. I was going to start saying that like I'm reading this stuff and I'm already getting confused, right? I'm seeing this like IO address plus 0x52, and that's not in this register table at all. But yeah, I'm pretty happy with that. So today we've like finished up like this like hacky, crazy assembly runtime code generation shit that we use for ISR handling, and then we started talking to PCI devices from nothing, and then we've proven to ourselves that we can like read and write, or not write, we can read memory associated with a specific device. And so I think that gives us all the pieces that we need to get moving with an RTL driver. And so I think I want to do some reading on like the RTL card itself and get back to that tomorrow. So thanks for watching. Pretty stoked on that. This is a good day, fun time. Yeah, thanks for watching. Catch you on the next one. Bye.